a sample gravitation problem. And here it is. So how quickly is the International Space Station moving while in orbit? And we are going to be given in this problem the altitude of the station's orbit. So its distance, average distance above the surface of the Earth. And we'll be assuming that it's like a homework problem. So we have access to standard information like the mass and radius of planet Earth. Usually is in like the inside cover of your book if you have a paper version, or in one of the appendices if you're looking at the digital one. Okay, how would we approach this? Okay, well, one thing we would have to assume is that, say there's planet Earth, and there is the International Space Station. We would generally have to assume that it's in a circular orbit around the Earth, okay? Because then we can bring our circular motion tools to bear. And it's actually a pretty good assumption. Technically, its orbit is just a tiny bit elliptical, okay? But only a tiny bit. So, next, okay, we have to think about, now that we've established that it is moving in a circle, we know that we can break out F sub c is equal to mv squared over r. And if you remember from circular motion, we want to then consider what forces could be causing this center-facing net force, and thus the center-facing acceleration that we know has to exist to bend its velocity into this circular shape. Well, it's the International Space Station. There's no normal forces or tensions. There's nothing, no strings attached. It's just gravity that's pulling on it. And gravity that would be acting towards the center of the circle, right? Because we know from our previous discussion of gravitation, that gravitational forces are attractive, and they act along a line that connect the centers of mass of the two objects. Here, the Earth is pulling on the International Space Station. Technically, the International Space Station is pulling on the Earth, but the Earth is so massive compared to the International Space Station that the Earth moves not even a little bit, and the International Space Station is highly influenced by the force of gravity that the Earth exerts on it. Okay, so our force is due to the gravity of the Earth, and so we can set centripetal force equal to that force of gravity. And we learned that when we're dealing with objects that aren't near the Earth's surface, we need to use the more general form of gravitational force, which is Newton's universal law of gravitation. And that is equal to G, M, I'll call that the mass of the mass of the space station, and M sub E, so the two masses of the two objects that are interacting via gravity. And we divide that by the distance between their centers of mass. It's worth putting that on the diagram, because if you were to just put in 409 kilometers for the radius here, you would get a astoundingly incorrect value for the velocity that we're looking for, right? So this r is going to be the radius of this circle, and that's also the distance between the center of mass of the International Space Station and the center of mass of the Earth, which is approximately at its center, okay? So this r, which is the radius of the circle that the space station is going in, and this r, which is the distance between the center of mass of the space station and the center of mass of the Earth, are the same value. So we can just call them r and be done with it. Now, the first thing we want to notice here is that we don't actually care what the mass of the International Space Station is, because it appears on this side of the equation and it appears on this side of the equation, so it goes away. It could be any kind of satellite. As long as it's not large enough to appreciably affect the Earth, like move it in some significant way, like if it's the moon, then technically you need to start thinking about other things. You have to solve the two-body problem. Although even the moon is relatively small mass next to the Earth. But anyway, getting off topic. For us, it's tiny compared to the Earth, so we can just cancel it out and not worry about it any farther. Now, we have an equation, let's write the simplified version, that just tells us that these two things must be equal. and we can cancel a copy of r from both sides. And then we can solve for v. Okay, so we have big G, mass of the Earth, over r, all square rooted to get v by itself rather than v squared. Now there's one extra little bit we should realize that we need to go after if we're going to solve this properly. Yeah, we can look up the mass of the Earth. We know what G is. G is just a constant. But what is R? Well, it's this distance, right? It's from the center of the Earth to the center mass of the International Space Station. So what that is the radius of the Earth, which would be like this part. And then it's also plus how high the space station is above the surface of the Earth. So this part is just the altitude of the space station. So what R is in this equation is radius of the Earth plus 409 kilometers. And we want to convert all of that to meters. If we do, we get, let's see, let's put in the accurate value of the radius of the Earth, which is 6,378 kilometers. Add 3 zeros in the end, and you've got that in meters. And then 409,000 meters for the altitude above the Earth's surface, which gets you a relatively large number. Let's see, what would it be? 67, 87, 000 meters. Okay. And then we can take that and substitute into this equation. When we do that, you should get that the velocity of the space station to maintain that orbit is going to be 7,663 meters per second. Now, is that real? Is that a good value? Is that accurate? Is that actually what the International Space Station is moving at? Indeed, it is. Well, caveat. It's like maybe a few parts in 1,000 off, okay? But it's really accurate for as simple as that calculation was. We just had to look up a couple of values, put in the altitude of the orbit, and suddenly we know exactly how fast it must be going to maintain that roughly circular orbit around the Earth. It's really fast, isn't it? Well, that's why they had to strap a rocket to all the different pieces and put it together up there, right? So orbital velocities, take away from this, other than the process of this problem, orbital velocities are colossal. They really have to be big so that you don't just fall back down to the ground as you go around, okay? That's, if you ever hear on the news, like a satellite or whatever, you know, there was a malfunction with its launch vehicle and it did not achieve orbit. Well, probably the rocket malfunction didn't give it enough thrust and thus didn't get it up to the orbital velocities that it has to have to avoid just kind of moving a little bit in the direction of the force of gravity and falling back down to the ground, okay? To give the satellite and the space station a really significant sort of sideways, parallel to the Earth's surface velocity if you're going to expect it to stay up there. So, okay. That's that problem. Let me know if you have any questions, and I'll see you for the next one.